Okay, this morning I started to tell you about Maxwell's discovery of something brand new in electricity and magnetism. And it was this effect that a changing electrical field actually causes a circulating magnetic field around it. I mean, we've already seen that if you take electric charge and have it flow through a wire, that current will generate that circulating magnetic field around it. But here, in this, in the kind of circuit that I described for you this morning, where the current is flowing onto these two plates, in between the plates, of course, there's no current flow at all, and yet you still get that circulating magnetic field that I described. And Maxwell realized that people had only seen one way to get that kind of circulating magnetic field before, and that was to have an electric current. Maxwell realizes there's two ways. And the second way is to have a changing E field, electric field. So let me sum that up by saying, let me draw a circle over here. And let's say we have a B field going around that circle, magnetic field going around the circle clockwise. Now, how can we get that? Well, like I said, there's two ways. Two ways to generate a circulating magnetic field. The first you've known about for a long time. What would you do? Let's say you've got a wire and you can put a current through that loop. Let me see. You would want it to go into the board, right? Okay. So electric current flowing through the loop is one way to generate the circular B field. Now the second way is to have an electric field that is changing through that loop. So changing E field through loop. So if you had a big ball of charge, I mean, if we spun a glass ball around really fast with rubbing a cat against it, and we brought it up to this loop, we would generate that kind of a B field, the same kind of B field we get from putting a current through the loop, just because we're changing the flux of electric field through the loop. Now, does this remind you of anything? Yeah.
How you can move a magnet to create an electric field?
Yeah, exactly. I mean, what Maxwell has discovered is something very much in parallel to what Faraday discovered back in 1831. when he discovered that he could generate a current through a loop by moving a magnet in and out of the loop, right? So if, I mean, just to remind you, if we now change this to an E field, okay, well, how do we generate a circulating electric field?
You could take a bar magnet and move it.
Right, okay, so that just means we need a changing B field through the loop, right? That will work. Now, is there any second way that you can create a circulating E field? I mean, there were two ways to generate a circulating magnetic field. We could have a electric current, or we can have a changing electric field. Now we're talking about creating a circulating electric field. One way is to have a changing magnetic field. What would be the parallel way, another way, to create the circulating electric field?
To have a magnetic force flowing through a loop.
Yeah, I mean, if we had, if we could have a magnetic current going through here, then that would seem to do it, right? I mean, if there was this perfect parallel between electricity and magnetism, what's wrong with that idea? There isn't any such thing as magnetic current. Okay, so because there's no, I mean, if there were isolated magnetic poles, okay, then you could take all these little, say, magnetic north poles, you know, and throw them through the loop, right? And that would do it. But there aren't any isolated magnetic poles, right? Every time you have a north, you always have a south. I mean, that's equivalent to, like in electricity, if every time you had a positive, you had to have a negative, and there was no net electric charge at all that you could ever put through a loop, then that wouldn't work. Then you couldn't have electricity either. So there is this difference between electricity and magnetism, and that there are electric charges, there aren't magnetic charges. So in fact, there's only one way to create a circulating electric field. Okay, but there's we have the two ways of creating the circulating magnetic field, and Maxwell has discovered the second. And so what he has discovered is, I mean, we already knew that a changing magnetic field generates an electric field circulating around it. Now he's shown the opposite, that a changing electric field generates a circulating magnetic field. Now, as far as the direction goes on the circulating magnetic field generated by a changing electric field, it's the same as the old right-hand rule for the current. If you just put your thumb in the direction of the change in the electric field and curl your fingers, okay, you get the direction of the magnetic field. Now, well, let me ask you a question here. See if you're following me. Okay, we charge this thing up. We hook the battery up. Current flows for a while until these plates are fully charged. Okay, then the current stops. Now, you still have an electric field here, but of course it's not changing anymore. So you're not going to get any B field, right? Okay. Now, you short out the battery. Okay, you just you take the battery out of the loop and just connect these wires. Now, what's going to happen? Daniel.
It's going to decrease?
Yeah, current's going to flow for a while until what?
Until it runs out. Or
Yeah, until there's no more charge left on these plates, right? So it's just going to discharge. All the positive charge that's piled up on this plate is going to run through to the other plate until they're neutral again. Okay, now, what's happening to the E field again? Okay, it starts out big, and it's just decreasing, right? What magnetic field is that going to generate?
Is it the opposite?
Yeah, it's exactly the opposite. But the reason I wanted to point this out is because I didn't mean to imply earlier that you can just stick your thumb in the direction of the E field and always get the right direction for the circulating magnetic field. You have to stick your thumb in the direction of the change to the E field. Okay, so even though the E field here is in this direction, it's getting smaller. So, I mean, the change is actually in the other direction. Okay, so you will have the because it's getting smaller, the direction that the E field is changing is in the opposite direction. Stick your thumb in that direction, then you'll get a B field that is going, out of the board here and into the board down here. Ben, you look confused. It's the direction of the change in the E field is what actually it's the change. It's not the E field itself, but the change of the E field that's actually causing the circulating magnetic field. The direction of the change in this case is toward the right part of the board, because if you look at the E field when you first short out your battery, okay, the E field up here, say, is like this magnitude. And as the current flows off of these plates, discharging the plates, the E field is getting smaller and smaller.
They start discharging.
Oh, why do the plates discharge?
So it gets smaller and smaller by discharging the plates.
Yeah, because the reason there's an electric field between these plates is because they're charged up. Okay, you've got a whole bunch of positive charge on this plate and a whole bunch of negative charge on this plate. If the plates were neutral, if they didn't have any charge, you wouldn't have any E field between them, right? So, but what happens when you short out the battery here, you're just allowing the charge to run off. You're allowing those plates just to discharge. So that means the E field is just rapidly getting less. So the change in the E field is in this direction, right? The opposite direction of the E field itself. Because, I mean, in order to get from this big E field to this little E field, you have to subtract part of the E field, right? So
Two opposing sides.
it's, I mean, the difference between this E field and this E field is, if you take this one, let's put numbers on it just to make it clear. Let's say this E field, we're going to call this magnitude 10. Okay, and we're going to call this one magnitude 4. Okay. Now, what has the change of that E field been? Well, if you take the final E field and you subtract the initial E field, you get the change, right? Okay. Well, that's a 4 minus 10. Gives you minus 6. Okay, the fact that that's a minus sign means the change is in the opposite direction of as the E field. Okay. Yes, Evan.
If you have the B field, is it sort of opposing the change in E field, like the way when you have it with Faraday's?
No, it's not the same effect. Let me see. It's, I mean, the way you can think of it, if you think of it in terms of this example, the B field is inside these plates is always in the same direction as it is outside the plates. So one way you could always figure out what direction it has to be is just by figuring out what direction the current is going on the outside the plates. It's yeah, there's no it's not opposing the change the way that the way that Faraday figured out what the direction of the other the circulating E field had to be. Okay, now, Maxwell, strangely enough, didn't actually discover this new effect in the way that I just described. He had a different approach to discovering it, which I'm not going to try to describe in any detail, but I do want to tell you one thing about his approach because it tells you, it says something really interesting about mathematics. I told you when I started into Maxwell that he was a brilliant mathematician, and one of his major goals was to take Faraday's views on electricity and magnetism, what Faraday had discovered, and translate them into mathematical terms, which Faraday hadn't done. And when Maxwell read Faraday, Faraday was constantly talking about these electric and magnetic field lines and so on, but he wasn't writing equations. But when Maxwell read Faraday, he saw that you could take Faraday's language, his verbal descriptions of the behavior of these electric and magnetic fields, and translate them into mathematical terms. And that's what Maxwell did. He actually came up with the equations in terms of electric fields and magnetic fields that physicists still use today. Maxwell came up with the complete theory of electromagnetism. No basic discoveries, fundamental new laws of electromagnetism have been discovered since Maxwell's time. He completed the theory. Okay. But when he first put these equations together, he noticed something odd about the equations and a certain inconsistency, because he found that there was an operation that he could do on a perfectly legal mathematical operation that he could do on one of the equations that would lead to a contradiction. In other words, if you look back at what Ampere and Faraday had known, there was Maxwell found that he could read their stuff, and he could come up with an equation that related a circulating B field, okay, to the electric current generating it, okay. Now, when Maxwell discovered that there was, like I said, a certain mathematical operation he could do that would make this side of the equation go to 0, but that would not make this side of the equation 0. So what the heck? There's got to be something drastically wrong here, right? I mean, he hasn't done anything. I can't describe this mathematical operation to you because you need to know differential and integral calculus. But he just noticed that there was a mathematical inconsistency in the equation. And then he figured out, well, what would make this inconsistency go away? And sure enough, it turned out to be just this effect that I described for you, that if there were another way of generating a circulating magnetic field other than just having a current go through the loop, if there were a second way of doing it with a changing electric field, then the equation became consistent again. So that's, I just wanted to tell you about that because it's a fantastic illustration of the power of mathematics. I mean, this is a discovery, at least this approach to discovering this crucial missing term in the electromagnetic equations is something Faraday could never have done because he didn't know the mathematics. But Maxwell made this discovery precisely because he was expert in differential and integral calculus. And so he could notice, he could cast the ideas in mathematical form and then notice this kind of mathematical inconsistency. So that's just something for you to keep in mind during math class. If it ever seems like it's getting a little dry and unmotivated to you, remember that there's all kinds of exciting stuff I'm leaving out of this course because you don't have enough mathematics yet. Okay, 2 minutes left, and I was planning on, is that right or no? Quarter two, oh good. Okay, I thought that went too fast. Okay, Maxwell makes another major discovery here. So let me go on to number 2 here. Let's just call this Maxwell's second great discovery. Maxwell, once he has this, this other term in the electromagnetic equations, and he knows that a changing E field creates a B field, in addition to what Faraday discovered about a changing B field creating a circulating E field. Maxwell realizes that this has a tremendous implication. Think of it this way. Let's say we have a charge. Symbol for electric charge is Q, remember. And let's say we, I don't know, we just started shaking it up and down. Well, what are we going to be doing? I mean, let's say if when we move this charge up, okay, that's like having a current in that direction, right? Now, if I had a current in that direction, what is that going to cause? Yeah.
A circulating B field?
Yeah, it's going to cause a circulating B field for one thing. Let me see, if I have a current in this direction, you'd have a B field, say, going into the board here, right? Okay, now, is the, what's this going to cause?
Shouldn't that be in the board? Shouldn't that be the X because it's got.
Oh, sorry.
Wait, no.
Wait, yes. Now, well, that caused the B field to change here, right? What's that going to cause now?
An E field?
Yeah, it's changing B field is going to cause a circulating E field, right? Okay, so circulating E field, say, let me see, the way I've drawn it, increasing the flux into the board here, the E field would generate to oppose that. You would actually get an E field, say, over here, coming pointing up.
How did you get that?
Because if you have a B field that's increasing into the board here, okay, you would, if you had a loop here, you would generate a current that would oppose that. Right? So the current would have to be in the counterclockwise direction to oppose that change in the B field. Okay. Does that make sense to you, Nick? Nope. You didn't get it. Oh my God. Okay. Yes.
What if that was an E field right there?
Oh, which one?
The where the B is.
Yeah. Okay.
If that was an E, would that mean that the arrow pointing up with the E, would that be a B?
Well, if you had an E field increasing into the board, then that would cause a circulating B, right?
Oh, okay.
It would actually be in the opposite direction as I've drawn this E. Well, let me first get, I mean, before we worry about directions, let me get the basic idea across here. What Maxwell realizes is you shake a charge like this, you're going to create, for example, a changing B field, okay? Which is going to create a changing B field creates a changing E field, right? Right? That's what we've been talking about. A changing E field creates a changing B field, which creates a changing E field, which creates a changing B field. Dot, 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 dot. Exactly. So Maxwell realizes that once he has this missing piece of the puzzle that people didn't have before, that they didn't know that a changing E field created a B field. Once he has that, and he knows the reverse is true from Faraday, then he sees, geez, all you have to do is start with an electric charge and shake it up and down, and you're going to get this electromagnetic wave, okay, that consists of oscillating B field in one direction and an oscillating E field in the other direction. And they'll just continue to propagate down the line. I mean, that's the main idea. Even if you have a hard time working out the directions here, you can see that all you need is this pair of ideas, that a changing B field creates this circular E field at right angles to it. Okay, and then the opposite is true too, that a changing E field creates a circulating B field at right angles to it. Then once you start shaking an electric charge, you create that changing B field, which creates the changing E field, which creates the changing B field, and so on and so forth, all the way down the line. Now, Maxwell was so clever that he could use these equations of electromagnetism that he came up with, which I haven't really shown you because they're differential and integral equations. But he could actually use these equations to show that first of all, that it has to lead to this wave, and secondly, he could actually derive an equation for the wave and figure out how fast it had to travel. So he does this. He starts with the equations of electricity and magnetism that you've already seen. Remember that if you think back on Coulomb's basic discovery of the force between electric charges, remember that we showed that it was an inverse square law force. Okay, so the equation, I start waving these things around and then they dry out on me, I think. If you have just a stationary charge here, let's call it a positive charge, okay? Well, the E fields just goes out from a positive charge, right? In all directions. So these are the lines of E. Well, according to Coulomb, they fall off as the inverse square of the distance, right? So, but this should look familiar to you. If I write the equation for the E field, remember I introduced this constant K sub E in Coulomb's force equation, and of course the force is just proportional to the strength of the charge and inversely proportional to the distance from the charge, right? The squared. Okay, so that's the equation for the E field. Now, if we have a current going through a wire, the equation for the B field from that I called, let me see, I introduced a K sub M, if you remember, when we talked about the force between currents that Ampere discovered. So these are just constants, these K's, that tell you the magnitude of these the strength of these forces. You know, like big G was the constant in the gravitational equation. Okay, so, and remember, how did the B field depend on distance as you went away from the wire? Do you remember? Troy?
It was directly proportional.
Inversely proportional to R, but first power, that's what you meant. Okay. Right. You know it gets weaker as it goes away from the wire. Okay. So we had these two equations for, you know, the electric field from a charge and the B field from a current. Well, Maxwell uses his equations of electromagnetism to derive an equation for this oscillating electromagnetic wave. Okay, and these, of course, these constants enter into his equations, and he comes up with an equation for the wave where he can derive the speed of the wave, and it turns out to, let me call the well, speed of EM wave that Maxwell derives turns out to be equal to the square root of the electrical constant divided by the magnetic constant. I mean, 2 times the electrical constant divided by the magnetic constant. And this is in units of meters per second. Okay, so if you're working with meters and seconds and kilograms, this is the values of these constants are, let's see, 9 times 10 to the 9th for the electrical constant, so a big number. For the magnetic constant, very little number, 2 times 10 to the negative 7th. Okay, if you, I don't know how many of you have exponential notation, but this is 10 to the minus 6th is like a millionth. Okay, so this is less than that. 10 to the 9th is a billion. So this is 9 billion, and this is less than a millionth. Okay, so, well, we can just plug these numbers in now to this equation and get the speed of this electromagnetic wave that comes flying out from this oscillating charge. Okay, so turns out the numbers are really easy, right?
Yeah.
So this is, if you work this out, you get square root. This comes to, doing a little math in my head, I can see that this comes to 9 times 10 to the 16th. 3 times 10 to the 8th meters per second. And for those of you who don't like exponential notation, I'll put in the zeros. Well, let leave off 3 zeros so I can write kilometers per second here. Okay, so 300,000 kilometers per second is the speed of this electromagnetic wave. Now, what does that turn out to be in miles per second?
Oh, you gonna make us do that? Okay.
I should make you do it, but I'll do it off the top of my head. In miles per second, it's 186,000 miles per second. Hey is right. Does that remind you of anything? Why the heck would it be the speed of light? That's bizarre. Why would it turn out that way? Did it give you any ideas, Daniel? Because it's a funny world. Yeah, okay.
It's light.
Because this is light. This crazy electromagnetic wave that you get from shaking this charge is light. That's what light is, an electromagnetic wave. Nee.
How come if you do that, it doesn't get all shiny?
Oh, it does, if you shake it hard enough. That's exactly what's going on in the sun. A lot of charges are getting shaken up really, really hard. Now, the now I'll show you what happens when you shake it more slowly next time, and that's the experiment that people did to actually prove that this was true. I'll describe to you next time, but you can see this is an amazing result that just comes out of Maxwell's mathematics. And so I'll follow up on that next time.